Now optics lesson 46. Now let us do the theory part of optical instruments. Optical instruments. Now before we proceed, let us understand this. Objects that are close to us but small. Those objects that are close to our eye but are very small, we cannot see them, are small in size and may not be visible to the naked eye. For such things, for such objects, we use optical instruments, and that instrument is called a microscope. For example, if you just take an ordinary convex lens and start reading your newspaper, you hold the lens very close to the newspaper, and that lens is called a simple microscope. It is of two types, simple microscope and compound microscope. Let us do the theory part of simple microscope. A simple microscope, it is a convex lens of small focal length. Look, this convex lens of small focal length. I am watching from this side. This is my eye. Of course, the eye is not so far off. The eye is very close to the lens. It is a convex lens of small focal length, and the object is placed between focus and the optical center of the lens. Look, this is the object AB. This lens has a focus on this side and a focus on this side. C is the optical center. The object AB is kept between C and F. So a ray going parallel from here, parallel to the principal axis, passes through focus, as explained earlier, and a ray passing through the center of optical center of the lens goes undeviated. These two rays on this side, they are diverging, so they will not meet on this side. So when produced backwards, both the rays when produced backwards, they appear to come from A dash. So two rays were taken from A, one like this, one like this. After refraction, both of them appear to come from A dash. Therefore A dash is the image of A. So therefore A dash B dash is the image of AB. This is a virtual image. If you put a screen here, this image won't be caught there. But when you are watching from this side to this object, you are not actually seeing the AB, you are watching the image of it, that is A dash B dash, which is magnified. Therefore it is called a simple microscope or a magnifying lens. Let's see the optical center of the convex lens. This height AB, let it be h, the height of the object. From A dash to B dash, let it be h dash. A dash B dash is the height of the image. F is the focus. And now let x from C to B is the object distance. Light is going this way, so the object distance from C to B will be negative. From here to here, I write it as capital D. CB dash is the image distance. Why I have written capital D? Where D is called the least distance of distinct vision for a normal eye, which is 25 centimeter. What do you mean by this? When you look at an object which is very close to your eye, the eye lens is not able to adjust the curvature of the eye lens. This is your eye. If an object is very close to the eye lens, which is a liquid lens, has to adjust its curvature, this curvature and this curvature, so that the rays gets focused at the retina. But there is a restrictions to that. So the minimum distance from which your eye can see an object clearly without much adjustment to its radius of curvature of the eye lens, that distance is called the least distance of distinct vision for a normal eye, which is 25 centimeters. So I have taken it as D. Now look at a triangle ABC and A dash B dash C. ABC and A dash B dash C. They are similar. How similar? This is 90, this is 90. This is the common angle. This is the common angle, and the rest angle, this should be equal to this, because the sum of the three angles is in a triangle is 180. So the sides are proportional. Therefore, a dash b dash by ab, a dash b dash by ab will be cb dash by cb, cb dash by cb. This is equal to h dash, this is equal to h, cb dash to this side. Light is going this way, this direction is positive. So any distance measured along this direction is negative. So d is negative and x is also negative. So minus minus cancels. I am left with a d by x. Now what is this? The size of the image by size of the object. Therefore magnification. So I write it as m. So is equal to d by x. Now use the lens formula. 1 by v minus 1 by u is equal to 1 by f. So your image distance v, your image is here from C to B dash, opposite to the direction of light is minus t, Your object distance of object from center of the lens, optical center, is CB, opposite to the direction of light. Therefore is again minus x. So is equal to 1 by f. So minus this becomes plus 1 by x. I bring 1 by minus d to this side. So this becomes 1 by f plus 1 by d. So this is the value of 1 by x. Now look at this. Your magnification m is equal to, now look at this. Sorry. Now look at this. Some part was not visible. The paper was little below the focus. So h by h dash is equal to minus d over minus x, that is d by x, and this is nothing but the magnification, because image size by object size, that is equal to d over x. Now use the lens formula. 1 by v minus 1 by u is 1 by f. Now v is negative, u is negative, because image is here from C to B dash is minus t, from C to B is minus x. Both are opposite to the direction of light. So minus t minus x, this becomes positive. I bring this 1 over minus d to this side. So this becomes 1 by f plus 1 by d. Now if you look at this, magnification is d over x. That can be rewritten as d into 1 over x. So for 1 over x, I substitute this value, 1 by f plus 1 by d. So I take d inside, this becomes d by f. I take d here, so d by d. So this becomes 1 plus d by f is your magnification when the image is at the least distance of distinct vision. Now what is this d is explained here, called least distance of distinct vision. Our eye lens adjusts its curvature to change its focal length, so that the image is always formed on the retina. If the object is very close, there is difficulty in adjusting the curvature and the image appears blurred. And it is found a minimum distance called d is the least distance of clear vision, which is 25 cm for normal eye.